Hi, I'm Luz Diaz.
And I am Uyi Irabo, and we are Group 3.
Thank you for joining us in our discussion of our project, Algorithms and Heuristic Approaches for Solving the 8 Puzzle and N by N Variants. Let's get started. This project focuses on exploring different algorithms and heuristics to solve the classic 8 puzzle problem and extending these approaches to larger puzzles. Our goal was not only to implement these algorithms, but also to compare their efficiency and performance metrics. Let's start by discussing the problem at hand. The 8 puzzle problem is a sliding puzzle that consists of a 3x3 grid with 8 numbered tiles and 1 blank space. The goal is to rearrange the tiles in numerical order by making use of the blank space. Each tile can only move horizontally or vertically into the blank space. This simple set of rules creates a complex problem space as the number of possible states increases rapidly. Here, you can see an example of an initial state on the left and the goal state on the right. The task is to move the tiles from this initial mixed state to the ordered goal state. What makes this problem interesting is the number of possible moves and paths that could potentially solve the puzzle. It's not just about finding any solution, but finding the most efficient one. Imagine a small child playing with this puzzle. They may move tiles all day, but if they don't have a strategy, they may never solve the puzzle. We want our program to not only reach the final state, but do it in the fastest, most efficient way possible. Here we can see an animation of a sample puzzle being solved. This is actually the resulting path calculated by our program given the initial puzzle. As you can see, the puzzle is solved quickly with only 23 moves, which is the minimum number of moves required to solve this particular puzzle. We encountered several challenges when it came to this project. Our first challenge was choosing optimal algorithms and heuristics to balance time and memory usage, given the large number of possible states, particularly as we scale to larger N-by-N puzzles. This was an important decision. Another important aspect was selecting the appropriate data structures to represent the states of the puzzle. We started out using NumPy arrays, but later opted for two-dimensional tuples instead, due to their immutability, hashability, and memory efficiency. This allowed us to easily store and check states, as well as use them as keys in dictionaries. It also gave us the confidence that states couldn't be unintentionally altered. It was also a priority for us to create an intuitive, user-friendly interface. We wanted users to comfortably interact with our program, selecting algorithms, entering custom states, and reviewing solutions. The interface had to be simple but effective, allowing for experimentation with different algorithms and heuristics. Scaling the puzzle for N-by-N states proved to be the biggest challenge, particularly in terms of time and memory constraints. As you can see, the number of states in a 3x3 puzzle is about 180,000, but 4x4 quickly jumps to over 10 trillion, and 5x5 has more zeros than I can name. While our algorithms work well for the 3x3 puzzle, the computational complexity of these larger puzzles made them difficult to solve efficiently with the resources available. For this reason, while we still allow the user to choose a larger puzzle, we did not perform further testing on them due to time constraints. If you choose to test larger puzzles, we recommend a custom start state with only a few tiles out of place to avoid excessive wait times. Another challenge we encountered was unsolvable puzzles. An inversion is any time a higher number precedes a smaller number. The easiest way to find the total number of inversions is to list out all of the numbers excluding 0. In this case, we have 1, 3, 2, 4, 5, 6, 8, 7. Because 3 is greater than 2 and 8 is greater than 7, we can say that this example has 2 inversions. For an odd-sized puzzle such as 3 by 3 or 5 by 5, an odd number of inversions means this puzzle is unsolvable. There is an additional step if the puzzle is even-sized, such as 4 by 4. In this case, we need to determine whether our blank space is an odd or even row. Don't forget that the first row is index 0, so the second row is technically row 1 and therefore odd. We found this to be confusing, so we chose to simply count from the bottom up instead. If the number of inversions is even and the row is even, then the puzzle is unsolvable. Likewise, if the number of inversions is odd and the row is odd, the puzzle is also unsolvable. So let's take a look at our solutions and contributions. We implemented various informed and uninformed algorithms to solve the A puzzle problem. We had not seen this many algorithms and heuristics tested all in one place this way in any of our research. We also included the option to do n by n size puzzles, which we had not yet seen in our research. We created a straightforward interactive user interface, which allows the user to select puzzle size, choose between preset, random, or even create a custom puzzle, and choose from a variety of uninformed and informed algorithms. If they choose A star, then they can select their heuristic of choice. We wanted to be able to collect large amounts of performance data automatically, so we wouldn't have to manually solve puzzles with different algorithms and heuristics. We incorporated the option to do this and export the results to a CSV file. We then used this data to perform our own analysis and comparison of algorithm performance. Here we can see a chart of the workflow for our program. We begin at the top, where the user is prompted to choose between the default 3 by 3 puzzle or a larger puzzle. After making their choice, the user can then choose their start state. They can select one of the 3 provided preset options, generate a random puzzle, which the program automatically tests for solvability and continues only once a solvable puzzle is found. Or they can create a custom puzzle, which the program will not only test for solvability, but also for an incorrect input, such as a missing 0, repeated numbers, or numbers out of range. If any of these issues arise, the user will be prompted to enter a different start state. At this stage, we are also given the option to automate data collection. If this option is chosen, the user will be asked how many puzzles to solve. The program will then automatically run through the number of puzzles defined by the user using all of the available algorithms and heuristics except depth-first search due to its inefficiency. A CSV file will then be created if it doesn't already exist, or if the file exists, the new results will be appended. Once the user chooses their algorithm, if they chose A star, they can now choose from the 4 provided heuristics to solve the puzzle. The puzzle will now be solved and the resulting metrics will be printed. This includes the algorithm and heuristic used, the amount of time it took to solve, the total attempted moves, and the number of moves in the final path. The user will now be prompted to choose between solving the same puzzle with a new algorithm, solving a new puzzle, saving the final path states to a text file, or exiting the program. Choosing to solve another puzzle, whether it's the same one or with a new algorithm or a new one, will assume the same size puzzle. Now that you have a clearer picture of how our program works, let's dive into the algorithms we use to solve the n-by-n puzzle problem. First, we have breadth first search, or BFS. BFS explores all possible moves level by level, starting from the initial state and progressing outward. It guarantees finding the shortest path to the solution, but it can be memory intensive because it stores all possible states at each level. Next is depth first search, or DFS. DFS explores each possible path as deeply as possible before backtracking. This approach can be more memory efficient than BFS, but it doesn't guarantee the shortest path. There's also the risk of getting stuck in deep, irrelevant branches, especially in large puzzles. Iterative Deepening Depth First Search, or IDDFS, combines the benefits of both DFS and BFS. IDDFS performs DFS with an increasing depth limit, effectively combining the depth-first approach with the breadth-first guarantee of finding the shortest path. It strikes a balance between memory usage and completeness, making it more efficient for deeper search trees. Finally, we implemented the A-star search, a more sophisticated algorithm that uses heuristics to guide the search toward the goal. The A-star algorithm evaluates paths by combining the cost to reach a state with an estimated cost to reach the goal, making it more focused than BFS or DFS. To enhance the A-star algorithm, we employed 4 different heuristics, which we will further discuss in the following slide. We calculate the Manhattan distance by summing the horizontal and vertical distances that each tile needs to move to reach its goal position. So how do we calculate that? We can find the Manhattan distance by finding the difference between x values of the start and end states and adding it to the difference in y values of the start and end states. We will not include the blank space for any of our heuristic calculations. This example has 3 tiles out of place. We will calculate our Manhattan distance heuristic by adding the results of all 3 tiles. We can see that tile 5 is at position 2, 1, and its goal state is at 1, 1. Using the formula, we can see that it is 1 move away from its goal state. Similarly, we can use the formula or this visual representation to see that tile 6 is also 1 move away from its goal state. The 1 tile is the furthest away from its goal state. Here, we can see that we must move 2 spaces to the left and 2 spaces up to reach our goal state. This tile is 4 moves from its goal state. The Manhattan distance for this example is adding all of these together to get 6. Hamming distance is simple to calculate. We simply count the number of tiles that are out of place. In this example, all 8 tiles are different from the goal state, so the Hamming distance is 8. While Manhattan distance is akin to walking blocks in a city, Euclidean distance is as the crow flies, or the straight line distance between the start state and the goal state. We can find this distance using the Pythagorean theorem. The Euclidean distance is equivalent to the hypotenuse of a triangle, where a and b are the difference in x and y values. This example has 2 tiles out of place. The distance for tile 1 from its final state can be calculated using the formula, and we see that the answer is 2.83. The second tile, 2, simply moves 1 space to the right, and its distance is 1. We add these together to find the Euclidean distance of 3.83. Finally, we have the Chebyshev distance, which simply takes into account whichever is larger, the difference between x values or y values of the start and end states. In this example, we have 1 tile out of place. The 4th tile must go left 2 columns and up 1 row to reach its final state. Because 2 is greater than 1, our Chebyshev distance is therefore 2. I will now hand it over to my partner Uyi to discuss the performance evaluations of our program.
Thank you so much, Luis Diaz, for that outstanding presentation. My name is Uyi Irabo. I will now continue the presentation. This slide shows a table of the performance evaluation of the different algorithms, showing the average time taken per puzzle and the total moves required to solve the puzzle. Our performance evaluations show that A star with the Manhattan distance heuristic outperformed all the other algorithms in both times and number of moves. Hammering distance was the least efficient among the informed searches, and IDDFS was the slowest, requiring the most moves. BFS was not time efficient, but was reasonably space efficient for an uninformed algorithm. This slide visually represents the average time taken by each algorithm using a bar chart, which further emphasizes the superior performance of A star with Manhattan distance in terms of time efficiency. The average time per algorithm shows A star with Manhattan distance being the fastest, and followed by A star with Euclidean distance, the Chebyshev distance, and Hamming distance. BFS and IDDFS took significantly longer time. Also, this slide uses a bar chart to visualize the average number of moves required by each algorithm, highlighting that A star with Manhattan distance also requires the fewest move on average to solve the puzzle. The average total moves per algorithm indicates A star with Manhattan distance requires these few moves, followed by A star with Euclidean distance, the Chebyshev distance, and Hamming distance. BFS and IDDFS require significantly more moves. Now, let's discuss the key findings from our experiment. Our experiment revealed several interesting findings. All algorithms successfully produce correct solutions, but A star with Manhattan distance stood out as the most efficient in terms of both time and moves. Hamming distance proved to be the least effective heuristics for A star. IDDFS was particularly slow and inefficient for solving the eighth puzzle. Larger puzzles presented computational challenges due to the exponential increase in possible states, requiring more testing for future improvements. While BFS was slower than A star, it was notably more space efficient than IDDFS by using significantly fewer moves. This research was focused on 3 by 3 puzzle but our code is designed and developed to handle larger n-by-n puzzles. However, further testing is required for larger puzzles due to the increased computational complexity. Now, let's illustrate how our program solves the puzzle. It begins with user input, where the user specifies the puzzle size, initial state, and desired algorithm. The program then executes the chosen algorithm to search for a solution. If a solution is found, the final part and relevant statistics are presented to the user. The user can then decide to save the result to a file or try another puzzle. This can continue until the user decides to finally exit the program. In conclusion, our research demonstrated that A star with the Manhattan distance heuristic is the most efficient algorithm for solving the 8th puzzle. BFS and IDDFS were considerably slower, and DFS was so inefficient that we excluded it from our large scale testing. Larger puzzles present significant computational challenges due to the exponential increase in the number of possible states. Looking ahead, we have several ideas for future improvement. We would like to add graphical interface to visualize the solution path, making it easier to understand the steps involved in solving the puzzle. We also plan to leverage more powerful hardware to exploit the capabilities of our program on larger puzzles. Additionally, we aim to implement more advanced algorithms and heuristics to further enhance the efficiency and performance of our ACE puzzle solver. I would like to thank you for your attention and also thank Luis Diaz for our effort and contribution. We hope you found our presentation informative. We are open to any question you may have. Thank you and have a great day.